Sir, we are live now. I'm
Yeah.
going to mute myself and turn my video, sir. You can start the session, sir.
Okay.
Thank you, sir.
Okay. Hello and welcome to the live session of the NPTEL.
Sir, we are live now.
Yes.
I'm going to mute myself and turn my video, sir. You can start the session, sir.
Okay.
Okay. Thank you, sir.
Hello and welcome to the live session of Machining Science NPTEL course. So I hope you all have enjoyed going through the course. The idea of this live session is to clarify any doubt that you will be having or you have, you have faced while going through the course and while going through the lectures as well as while repeating that. So you can write your questions in the chat box, and I'm going to answer to those questions one by one. Okay. So we have already collected two questions. One is that Mr. Arvind is asking that AutoCAD is very important. Yes, I agree. The AutoCAD is very important. Now the AutoCAD has its own place. Okay, like we use the AutoCAD for the drawing purposes. All right. Now in this course, there is no provision of going through the AutoCAD theory or something. So therefore, I have not touched upon the AutoCAD. However, I agree with you, Arvind, that AutoCAD is very important and you should learn that. But that has its own use, you see, it's not in the machining. Second question, Saurav Majumdar is asking, what is the function of auxiliary cutting edge angle? So if I will set the auxiliary cutting edge angle very nearer to 0, like 0.5 degree, it can improve the surface finish, cutting tool strength, and also achieve large area for better heat conduction. Okay, so to answer your question, Mr. Majumdar, Saurabh, overall the cutting edge angles, okay, it has the following significance. Once the cutting edge angles are changed, in that case, the radial force, which is trying to distract the tool from the workpiece, this is actually changing. All right. And this ultimately, if the angle is very high or angle is, let's say, not adequate, in that case, the forces will be very high and high in magnitude. And then there could be some sort of self-excited vibration, which we call as a chatter. So that is the main function of the cutting edge angle. And as you have pointed out, that the surface finish can improve. Yes, I agree with that. Surface finish can improve because we can actually reduce the amount of chatter. That is the basic thing about the cutting edge angles. Okay. Now, Mr. Amit Sharma, good morning. You are asking the term strain hardening. Well, strain hardening, as you can see, that in case of ductile material, when we have the stress-strain relationship or stress-strain curve, okay, when you elongate, in fact, it actually when you apply force, so it elongates. All right, and then the necking starts. So after the material has gone to the plastic zone, that means once the plastic deformation has started, after that the strain hardening taking place. Okay, and the strain hardening is the capability or the property of the material to withstand the force uniformly in spite of the because it necking started in ununiform change in the cross-sectional area. Okay, so that is the strain hardening, because the strain hardening takes place in that portion where you have the non-linear curve. You remember that after it has gone to the plastic deformation. Kindly explain the term strain hardening. So this is the one that I have explained just now. Amit Sharma, following question in the Google form. Any trick to understand or memorize the tool nomenclature? Yes, I have read that. See, there is a trick to understand. Yes, okay, because if we have good idea about the geometry and the spatial geometry particularly, and then if you go to the machine tool shop, you have to see the tool to understand that how these angles are given. Okay, so overall I will tell you that there are 3 sets of angles. Okay, and why 3 sets? Because see, for example, the rake angle. So there are 2 rake angles. Okay, depending on the system. For example, in case of ASA, okay, coordinate system, we have the back rake angle and the side rake angle. So those 2 angles have to be there so that the 2 inclinations are formed in 2 different sides. Okay. As you have understood, if you see the cutting tool, all right, you can see that there are different angles. Okay, there are chopped off in different angles in the rake face, in the back face, or in the flank face. So therefore, all these 3 surfaces are formed because of the in each surface there are 2 angles each, 2 rake angles, 2 flank angles, and 2 cutting edge angles. All right. So the trick in understanding is that you have to have a good spatial geometry concept, okay, which is taught in the first year of the BTech course, as you understand. And the trick to remember, there is nothing to remember, okay, memorize. If you can understand, then you don't have to memorize it. Okay, you will be knowing that which one is the back rake angle, which one is the cutting edge angles, okay, principal cutting edge angle, or the auxiliary cutting edge angle, side rake angle, and so on. Okay, I don't see any other question right now. So if you have any other question, you can actually put it in the chat box. All right. Okay, in the Google form, there is one more question. Dinesh, Mr. Dinesh, in the merchant's model, we have seen that the plastic deformation when the assumption is not considered to be valid. No, it's not very clear. Then we have, but we already know that this particular area is a part of area along. So why do we consider this assumption? Just 1 minute. It's not very clear. Let me expand that window. Maybe then it will come. Once again, in the merchant's model, we have assumed that the plastic deformation. Just 1 minute. We have assumed that the plastic deformation, when this assumption is not considered to be valid. No, I didn't understand why it has to be assumed that there is plastic deformation. See, Mr. Dinesh, in merchant's model, we have not assumed that this is the plastic deformation. Plastic deformation is a natural phenomena when the chip is removed. Okay, so you cannot assume, you don't have to assume, in fact, that this is a plastic deformation. If it is a ductile material, then the ductile material, as you start deforming, it has to go through the elastic deformation initially, and after that it will go through the plastic deformation before it segregates from the workpiece surface. Okay, so merchant circle diagram has nothing to do with the plastic deformation also. All right. When the assumption is not considered to be valid, then we have, but we already know that this particular area is a part of area along. Why do we? Okay, along chip tool contact length. Just 1 minute. Now it has come clearly. So now let me once again read that. In the Merchant's model, we have assumed that the plastic deformation takes place. Okay. So now I can read the full text. So in a thin zone, okay, that's right, over shear plane. When this assumption is not considered to be valid, then we have plastic deformation taking place over a finite area. So normal stress acts over this area during machining, and shear stress has nothing to do with this area. Again, when this assumption is not considered to be valid. See, let me go through this directly without having this shear strain and this plastic deformation. This part is not very clear from your question, Mr. Dinesh. So let me explain it to you that why it is not valid. Then probably you will understand that whether it will have the shear deformation or the shear stress or the normal stress. See, what happens is that when we start deforming the material, all right, in that case, the plastic deformation happens along the line where the atomic density is maximum. That we have already seen that in the crystal structure. Okay, so now that is called the slip line. Okay, and that slip line, in case of the ductile material or mild steel particularly, we have said that that has a particular angle. That angle is called the shear angle. Now this deformation, plastic deformation, happens in a zone. Okay, it does not happen in a plane, along a plane. It happens in a zone that I already said in the lecture. So that zone has a particular thickness. Okay, it cannot be zero thickness. It cannot be a plane, but it has been assumed for the simplicity in case of Merchant's analysis. That is one thing. Now, along the shear plane, there is a shear stress available. I mean, shear stress has to be applied so that the material can be segregated and the chip can be formed. All right, so that the particular shape, size, finish, accuracy can be obtained. All right. So there is a particular shear stress which has to be applied along the shear plane, so that the shear zone, okay, in the reality, so that the material can be removed. That is the answer to your question, first part. Then you said, but we already know that this particular area is a part of area along chip tool contact length. No, it is not the part of area along the chip tool contact length. Please don't make any mistake. See, the shear plane, you are talking about initially we have assumed that the plastic deformation takes place over a thin zone. See, the plastic deformation along the shear plane, okay, this is away from the chip tool contact length along the rake face. Chip tool contact length happens along the rake face of the tool, and it has nothing to do with the shear plane. It is away from the shear plane. Please don't get confused. Okay. Then, so regardless of whether we consider this assumption to be valid or not, there is normal stress acting on that area. Normal stress acting on that area, you are right, it is in that area where the chip tool contact length is measured. Okay, but it is not along the shear plane. Okay, shear plane once again is away from the chip tool contact length. All right. So then, of course, your last lines are not valid. Okay, because you are confusing with the chip tool contact length and the shear plane, which is not true. So if it is not true, in that case, your the last two lines are not valid. Okay. Now, Dinesh, your question again is that in the Merchant's model, we have seen that the plastic deformation takes place along the shear plane. It is because of the combined effect of normal force and friction force from the tool on the workpiece. Yes, it is. You are right in that, saying that it is whether the plastic deformation occurs because of the combined stress of the normal and the shear stress. Okay, that is true. Then you are asking, can you define what uncut thickness is in the oblique cutting? In the oblique cutting, the uncut thickness is not the depth of cut. Okay, uncut thickness is something which has not been cut and to be cut to change to be in the cheap thickness. It will be converted to the cheap thickness. All right. So unlike orthogonal cutting, where it can be assumed to be the same as the depth of cut, in case of oblique cutting, it actually gets multiplied or divided by some cos or sine theta. Theta is that tool inclination angle. Because the tool is inclined in case of the oblique cutting, so therefore, in case of oblique cutting, the uncut thickness is not equal to the depth of cut like in case of the orthogonal cutting. Okay. And also the difference between the uncut thickness and depth of cut. So I have already told you what is the difference. That in case of orthogonal cutting, it can be assumed the same. In case of the oblique cutting, it is actually getting multiplied or divided depending on how you are looking at this with the cos or sine inclination angle, tool inclination angle. Okay. Okay. There is no more questions. So Dinesh, I hope you are satisfied with this. So if you have any more question, you can still write it in this chat box of the YouTube live session. Okay. Yeah, so I have already opened Mr. Dinesh's question and I have answered to the questions. Okay. All right. Now, yeah, Mr. Amit Sharma, in machining, VF and depth of cut are variables, but these have to be selected on what basis we'll select this. Yes, these are very important factors. Okay. Cutting speed, feed, and the depth of cut. So in my lectures, I have actually told that how you are going to select the these three factors, that is particularly the cutting speed, feed, and the depth of cut. Let us once again clarify this and come to these factors one by one. Cutting speed. See, when you are increasing the cutting speed, what will happen is that you will have a faster rate. Okay, machining will go at a faster rate. That means production time will be less and the production rate will be higher. All right. Now, in selecting the higher V, that means you are trying to get more and more product in less time. That is good in one way, that your production rate will be higher. However, if you are increasing your cutting speed, your tool wear rate will be very high. Okay, and tools are very expensive. So in that case, probably you have to see whether your tool cost will eat up your profit in the higher production rate. You understand what I mean? That you have to judicially judge that how much you can increase the cutting speed so that your production rate will be higher as well as the tool wear rate will be lower. Okay, relatively. So that is one consideration that you have to give for the higher cutting velocity. Other considerations are that if you have the tool material, for example, if you have very soft tool materials, okay, like mild steel, for example, steel, tool steel, or the high-speed steel, these are relatively softer in comparison to ceramics, diamond tools, for example. So in that case, you cannot go for very high cutting speed because tool wear rate will be very high. Okay. Or if you have a very hard workpiece material, in that case also the tool wear rate will be very high. Okay. So there, if you use the soft tool material, in that case the tool wear rate will be very high. So you cannot have a very high speed. Now, other implications of high speed is that when you are having the speed higher, not only your production rate will be better, but your surface finish will be better. Okay, at a higher speed, normally the thumb rule is that at higher speed, surface finish will be better. Okay, this is because the friction will be less between the workpiece and the tool, because at higher speed. All right. So these are the considerations that you have to keep in mind while selecting the cutting speed. Now, the feed, okay, the feed is something that it can actually harm if it is if the feed the value is higher. So you cannot have a very high feed rate, because in that case the feed marks will be visible on the workpiece and the surface finish will be worse. So there is a certain range of feed that you can take. In my lecture classes, you can see the surface finish chapter. In the surface finish, I have discussed in details what is the effect of feed on the surface roughness. So basically, the feed actually, has an influence on the surface roughness or the surface finish. And the depth of cut. Depth of cut is less effective on the. It has less effect on the tool life. Okay. However, very high depth of cut will can break the tool, because there will be machining, that force required will be very high. So you have to judiciously again select the depth of cut, because higher depth of cut will have more forces required and the tool has to be stronger. Otherwise, the tool will break and the tool life will be less. Okay. So these are the basis on which you can actually select the parameters. These are called the cutting parameters: cutting velocity, feed, and the depth of cut. Okay, Mr. Sharma. All right, so there is one more question from Mr. Dinesh. In this course, everywhere we have considered the workpiece material to be perfectly plastic. Okay, that is, workpiece will not strain harden. So there must be an error in our calculations of forces and temperature involved in the machining process. I don't understand why. In perfectly plastic you have to have the error in the calculation. At the same time, we have made many assumptions in various types of models of machining. So, Mr. Dinesh, I don't find any relationship between this statement that we have made assumptions in various types of models and the statement that you have made earlier. That means there are errors in calculation of forces and temperature. I don't find any reason why we should have the errors. That is my response. Then you are saying that, so 1.1, which of machining models discussed in the course is the closest to the actual case? None of them. None of them. Okay. Where we machine manually. Also mention the order in which their closeness to actual case vary. How do you rectify this error? See, please try to understand. And I also told very specifically that whether you take up Merchant's model or you take up the Lee and Schaeffer, okay, or any other model, these models are helpful in understanding the mechanics of machining, but they are not in the reality. Because first of all, in the Merchants, let's say, for example, it says that the tool has to be sharp. Okay, tool cannot be sharp because as soon as the tool comes in contact with the workpiece, it actually gets, the tool nose radius gets formed. So it cannot have the sharp tool anymore. Now, along the chip tool contact length, the mu has to be constant as per the Merchant's analysis, but mu does not remain constant. That I have shown you in the analysis in the Zorev's model. Okay, so what I mean to say is that these assumptions do not make the model closer to the reality, and you cannot say that which one is closest and which one is farthest from the real situation. Okay, all are farthest. I mean, I can say that they are not real actually. So that's why we say that if we relax those assumptions, okay, there is some analysis that I have also shown in brief, that is the analysis for the oblique cutting, and there you can see that we are relaxing these assumptions of Merchants, because we are saying that this is no more a 2D case. It is the 3-dimensional case. The tool is inclined with respect to the cutting velocity vector. Okay, and they are not at 90° like in case of the orthogonal cutting. So therefore, with those relaxations, you can actually make the Merchant's model closer to the reality. Okay, but as it is, Merchant's model is not the reality once again, and it is far off from the reality because there are 8 assumptions, okay, without which Merchant's model will not be valid, and those assumptions take us away from the reality. That is my response. Okay. Yeah. So, Mr. Dinesh, I hope I have answered your question. Okay. So, if you have any other questions, so you can actually post it in the chat box. Okay. Mr. Amit, yeah, you said thanks. If you have any other question, you can actually put it in the chat box. I will try to answer to your question. I hope it is understood that how we select the cutting parameters, cutting velocity, feed, and the depth of cut. Okay. Yeah, Mr. Dinesh, I hope you have. Okay, you have another question, sir. I could not finish reading the entire course content. So we will post the material, Dinesh, and all others. To all others, there is a transcribed text being prepared. I am also hurrying up the NPTEL text section. Okay, there is a whole text section which works day and night, believe me, for the transcribed material, and that is being ready. Only for the first week it has been made. I have edited that, and it will be posted. So the material will be with you. Okay. I could not finish reading the entire course content. So how long will you be available on the course Google group? Mr. Dinesh, as I said, that entire lecture transcribed material will be available to you. And in case it is still not clear, so in that case, you can still put your question in the Google group, and we will answer to your question. Okay. Yeah, please post your questions to the in the chat box, and I will reply to your question. Okay, to your queries. Mr. Amit Sharma, yeah, you are asking that what is the role of dislocation in the context of strain hardening? See, the dislocation role is that it actually overall dislocation helps us in deforming the material. Okay, when we are deforming the material, if the dislocations are there, in that case, the dislocations or the defects, as we also call them, they actually move along with the atoms. Okay, I have given you some examples of missing atom, okay, misplaced atom, okay, and those are the point defects, interstitial defect, and so on. And as you have seen that if we are applying external force, okay, or the shear force, in that case, those defects also move. So you don't have to bodily move the entire lattice structure, and overall the force that you are applying will be less. So therefore, we said that it is actually not the g by 2 pi, which is theoretically obtained, but it is much less, maybe 1,000 times less than the g by 2 pi value which you get theoretically. All right, it is just because with the application of the force, those dislocations move. It has the relationship with the plastic deformation. Okay, Mr. Amit. Yeah, so if you do not have any other question, I once again thank you all very much for coming to this live session. And if you still have some question, you can put it on the forum, and I will reply to your questions. Thank you very much. Have a good day. Yeah, Mr. Murli, you are there.